Alright, so this is my Redstone Minecraft computer, and this is my sort of attempt to explain it. This is actually my third try, but hopefully uh, sort of improv explanation one take is going to do it. Um, so let's get started just with a basic overview of the big components, then we'll dive in a little deeper. So over here is the ROM. This is read-only memory, which means that we can read, we can see what's stored in it, but we can't store anything in it during the program, that is. And what this does is it just stores the program. So each row here stores one instruction, and then generally the computer just goes, instruction by instruction, line by line, reading the instructions, doing what they ask it to do. And so we have 32 instructions on that side, 32 instructions on that side, so we can store 64 instructions. These areas here are how we address them. So the way this whole thing works is we have an input, which is the address, which tells us which instruction we're looking at right now. So right now the address is 011000, and that's binary for 24. So if we go all the way out here to where binary 24 is, right there, you see that redstone line turns off, which turns all those torches on, which lets the instruction, go through the line and be read at the output. Okay, so that's the ROM, which holds the instructions. Let's look at the other components that help, execute those instructions. So first we'll look at the ALU. So this is the arithmetic logic unit. It does very basic math and logic functions, and it's sort of the heart of how our computer does computations. It's sort of the heart of our CPU. So it has two inputs. So up here we have one 8-bit input, 8-bit, 8 lines on or off. Down here we have another 8-bit input. And then we have a couple wires like that one and that one and that one leading into it to tell it what operation we want it to do. So it'll do a certain operation on those values that we can specify. And then the output is an 8-bit value over here. So whatever operation we just did, the output is 2. Let's see. Might just have taken the top value. So yeah, this operation just took the top value, took what we would call x, and outputted it. So we'll go into more detail on how we can specify what operation we want later, but that's that for now. And one more big thing we should cover before we dive deeper in is memory. So how do we store values? We already went over one type of memory, which is read-only memory. We use that to store the program. But we also have computation memory we use while we're doing, computations and executing the program and stuff. So we have two very small, fast types of memory called registers. So these store a single byte, a single 8-bit value, and we use them in between computations. So, if you're familiar with how Redstone works, you can probably see how this works by turning this top line on and then off. These locked repeaters will take whatever value is being inputted in there, and then they'll output it until they're set with a different value. So this is the A register, which is the accumulator or address register. And then this over here is the data register, and you'll see the data register is automatically feeding into the X input of our ALU, and we'll talk about how we can input values to the ALU in a little bit. But right now we've got the address register and the data register. And then, of course, we have the RAM, which is random access memory. And you can sort of think of this as 8 registers just sort of smushed together. We have an input line on the bottom, an output line on the top, and then we can have two sort of control bits. So we can use this line here to set. So when that line turns on, it'll take whatever value is being inputted and set it to the sort of byte in there that is indicated by this address register. So right now we're indicating address bus. We're indicating the 6th, number 6. So right over here, see, it's a similar address method as with the ROM, and we see that torch is on, so we're looking at number 6. So we can either store, write, or output read from number 6 using these two control bits. So the bottom one is store. If we turn that on, it'll store whatever values down here into the 6th bit of the RAM. And then this byte here, which you can see is on, is the enable, which enables the output. So when this turns on, the output, whatever is stored in the 6th bit, is outputted up top here. As you can see, we've stored the value 2 down there, and we can use that in computations and stuff. So that covers the basic big components associated with computations. One more thing, I just want to cover how output works. This isn't really too integrated into computing itself, but I just thought it's sort of fun and interesting. So the way this computer outputs, it only needs to output a single number at a time. So I've just used this last byte of the memory, and I just sort of steal that output off, and it comes out here. You can see we have 3 stored in that memory, and it comes out there. So the first thing it goes through, we need to convert binary to binary coded decimal, and binary coded decimal is a halfway step between binary and decimal numbers that we know, where each decimal digit gets 4 binary bytes. So, and you can sort of see that here. This first digit gets 4 bytes, and it'll go up from 0 to 9. Second digit gets 4 bytes, it'll go up from 0 to 9. The last digit only gets 2, but that's because it'll only be 0, 1, or 2. And the way we do that is with this implementation of the dabble algorithm. So I'm not going to go into a lot of detail, but there's an algorithm that computes how to transition from binary to binary coded decimal. It's really interesting, but it's also a little complex, so I'm not going to go into that here, but you can definitely look that up. Then we have 4 lines of binary coded decimal for each digit, and this way we just use a simple decoder on the bottom. Again, this is the same style thing that you saw with the address for the RAM and the ROM, and that just turns one line off of these lines. And in this case, it looks a lot like our ROM memory, where one line turns off and then it outputs that data. And these 7 wires just correspond to those 7 segments. So right now, we have 0, 1, 2, 3. So the torch indicating line 3 turns off that line here. These torches that indicate the looks like 5 segments that you need to display a 3 turn on. Those get fed up to the board, and there's 3. Okay, so I've gone over the big components, and I've gone over how the output works. Let's dive a little bit deeper into instructions, because if we really want to understand how this works, we sort of need to understand how instructions work. So, as you might have seen over there, each instruction is 16 bits, so 16, on or off, which in this scenario is indicated by torches. So right there, that's a 1, but there's a 0, 0, 0. So we have 2 types of instructions in our program, and I'm using a sort of simplified assembly or machine code copied from a chapter of a book I read that I provided in my original Reddit post. So let's just sort of explain that. So we have 2 types of instructions, data and computation instructions. Data instructions are a lot simpler. Let me go into those. So they just tell the computer, here's a value, hold on to it, you'll need it in a minute. So we can tell data instructions apart because their first bit is always 0. In this case, I'm going to use white for 0 and black for 1. The first bit is 0, which means that this is a data instruction. Then the rest of the instruction just stores the value that we want the computer to hold on to. Now, we do have all of these 15 bytes of space, but our computer only uses an 8-bit word size, which just means that that's the largest binary number that you can pass around and do math with. So really only these last 8 bits store a value that we want the computer to use. So this instruction corresponds to take the value 27, in this case, 110011, take the value 27 and hold on to it. And actually we hold on to it in the A register. So it takes it and stores it in the A register, and then we can do stuff with it after that. So if we were programming, you'd see this first line, at 27, we use this at for data instructions. This is how we would implement that, just at 27. Alright, these next two are computation instructions. You can tell because the first bit is on, so the first bit being a 1 means it's a computation instruction. You'll also see there's more parts to it, so let me get through that. These next two bits are actually unused. We just make them 1 by convention. They don't store any data, and it makes no difference whether they're on or off. This next bit, along with these next 6 bits, all these 7 bits, tell the computer what computation to do. So are you going to do the A register plus the D register? Are you going to just output a constant 1? What do you want the ALU to give you? And we'll talk about opcodes. So this is what's known as opcode. We'll talk about those in just a second, but we'll come back to those. Then we have these 2 more sets of 3 bits. These 3 bits tell us where we want to store the value of the computation. So let's say we've just calculated, D register plus A register. Where do we want to store it? Well, if this bit is on, it means we store it in the A register. If this one's on, it means we store it in the D register. And if this bit is on, it means we store it in RAM. You can have combinations, you can have all of them on, whatever. And then over here, these 3 bits are the jump condition. So this takes a little bit of explanation. Remember how I said earlier that when we're reading our program, we just go line to line down the program? Well, if we could only do that, that would be pretty limiting. If you know anything about coding, like control structures, it would just be completely impossible. No if-else statements, no while loops, nothing like that. So these jumps allow us to basically skip from one place in the code to another one, and then back to the beginning and whatever else. So the way we do that is by comparing the output of the computation to 0. So if this bit is on, we will jump if the output is less than 0. If this bit is on, we will jump if the output is equal to 0. And if this one's on, we'll jump if it's greater to 0. So in this case, they're all off, which means we just don't jump. If you want to jump unconditionally, you turn them all on, whatever. So yeah, let's look at one more instruction, and you'll see this one has a jump condition. So first bit, on, that just means it's a computation instruction. Next 2 bits are just on by default. They don't do anything. These next 7, these hold our opcode, and we'll come back to that in 1 second. These bits are all off, so our destination bits are all off, which means we don't store it anywhere. So this means it might be a little weird why would you do a computation and then just throw out the result, but we do the computation so you can compare it to 0. So in this case, if we do this computation and the result is equal to 0, then we'll jump. If not, whatever, we just keep going. Okay, so you have a basic idea of how instructions work now. Let's talk about opcodes. So we have these 6 bits plus this 1 extra bit. So let's figure out how that works. So the ALU has 6 bits that, of additional input where you can basically modify the inputs or the output of the function. So anyway, here, this is a table of opcodes and what they do. So here's the opcodes: ZX, NX, ZY, NY, F, and NO. So ZX and ZY, they take whatever is inputted to X or Y, and they just make it 0. Pretty simple. NX, NY, and NO, those invert either the X input, the Y input, or the output. Inverting, in this case, basically just means going through the binary number, and if there's a 1, make it a 0. If there's a 0, make it a 1. These are useful for stuff like subtraction and negative numbers and stuff like that. And then our last bit here is F. This is our function. So our ALU can do 2 things, 2 sort of base functions. It can add, and we have an adder on this side, and it can and, a bitwise and, which is on this side. What that means, add just adds the 2 inputs, and then and goes through each bit and says, is the first bit of X on, and is the first bit of Y on? If so, the first bit of the output is on, and so on. So we can combine these opcodes to do pretty varied things. So obviously we can just get straight up x, straight up y. We can do x plus y, x minus y. We can get constants like 0, -1, 1, negative x and y. You can increment and decrement by 1. So it's pretty versatile. Obviously it doesn't have everything. There's no, multiplication, but you can imagine implementing multiplication is just repeated addition. So it has very basic stuff, and we can write programs with that. So we can look back over here at the operations we had stored in these opcodes. You see 6 bits. So let's look at the opcodes. This opcode is 010011. So 010011, that corresponds to x minus y. 010011. There you go. And let's look at the next one. 001010. 001010 is just x. 001010. So that'll just output whatever is x. But what are x and y when we're doing computations? I mean, we have 3 areas of memory that we can take values from, right? We have the D register, the A register, and the RAM. But how do we decide which one's x and which one's y, and all of that? Well, so as you might have remembered, the D register is hooked straight up to the x input. So D is always the x input. Now, some of our computations don't need an x, so they probably set that ZX flag, like this one. It just takes y, and then we 0x right there. So we don't care what it is. And then y, so it can either be the A register or from the RAM over there. So how do we decide which one it is? Well, it's that final bit of the instruction called source memory. So this bit here that I've been skipping over, if it's off, we use what's stored in the A register. If it's on, we use what's stored in RAM at the address given in the A register. So how does that work? We have a little tool over here called a multiplexer, which basically is given 2 inputs and it picks one of them based on a redstone signal. So on the top here, we have the output from the A register, which right now looks like the value 6. And on the bottom here, we have the output from memory, which is the value 2. And then this redstone signal helps us pick to output the value 2. So if it's on, we do what's in M. If it's off, we do what's in A. And the A register, the address register, it's called the address register because it comes all the way over here and it feeds into the address for RAM there. So finally we can fully understand what's going on over here. I said this is x minus y, right? Well, what's x and what's y? Well, x is D always, and since this is on, the source memory bit is on, y is M. So this is really telling us calculate D minus M, whatever's in the D register minus whatever's in RAM, and then store it back in the D register. Okay? And then this one here, we calculated was just x, so that's just D. Take whatever D is, don't store it anywhere, compare it to 0. If it's equal to 0, then jump. Otherwise, do nothing. So before we dive right back into the computer and go into a little more detail on some stuff, I think it would be important to look at some actual code because, looking at these opcodes, seeing, x plus y and x plus 1, I mean, they don't seem all that useful. Like, it's hard to see how you would make a program out of just that. So I'm going to look into a little excerpt from the program I have running right now, which is the program to calculate prime numbers. And a really essential part of that program is checking divisibility, right? So taking one number and seeing if it's divisible by another number. Is 5 divisible by 3? No. I mean, duh. Is 4 divisible by 2? Yeah. So that's easy for us, but can we make a computer like this figure that out? And the answer is yes. So the way to do that is by repeated subtraction, because remember, we can't do division or anything. So repeated subtraction. So what we're going to do, if we're going to check to see if 5 is divisible by 3, we're just going to subtract 3 until we either get a negative number or a 0. If we get a negative number, that means it's not divisible. And if we get 0, then it means it is divisible. So why does that make sense? Well, if you get 0, that means you took out a whole number of 3's, and then you got to 0, which means that 5 is divisible by 3. But if you get a negative number, that means you passed the 0 without hitting it, which means it is not divisible by 3. So basically we're just going to keep repeatedly subtracting 3 from 5 until we either get a negative number or 0, and in those cases then we know the divisibility, and we'll jump to a different location in the code. So here's the code, sort of a mess. For this example, memory location 10, so address 10 in RAM, is N, which in our example is 5. And then memory location 11 is D, which is 3. So we're checking if N is divisible by D. Alright, so we use a data instruction to load the value 10, right? So we can address the right area of memory. We set the D register equal to M, which location in RAM? Well, it's 10, M10. So right now D is equal to 5. Now we're going to load the address that we want to jump to in RAM if it's divisible. So, we're going to jump way forward in the instruction memory if it's divisible. Then we're going to have a jump computation instruction. So if D is equal to 0, we jump to that place in memory. But it's not, it's equal to 5, so we just continue. Then we load a different place in memory where we want to go if 5 is not divisible by 3, and we jump if D is less than 0, if it's negative. Well, it's still not, it's still 5, so we go to, we continue on. We set D equal to, this value, small d, which is 9 at this point, so D equals M11. Load 10, now location 10, which we have it stored as N, which is storing our value 5, is equal to 5 minus 3. So now we're going to subtract 3 and then unconditionally jump back to the beginning. So we'll do it again. Now we have 2 for N because we've subtracted 3 one time, and still 3 for D. And we do the whole thing again, but of course N is still positive, it's not negative or 0. So we get to the end and we see we reset it, we subtract 3, and now we have negative 1. So we jump back to the beginning, load that value of N. Now we have D equals negative 1. Jump if it's equal to 0, it's not. But now D, being negative 1, is less than 0, so we'll jump to this location in instruction memory, YY, which you would replace with a value, obviously. And then that'll go to a different area of memory that, tells us what to do if 5 is not divisible by 3. So those, it's like 10 lines of code just to check if one number is divisible by another. It's sort of a lot, and it's very sort of obscure and hard to deal with, but that's what it's like programming at such a low base level with assembly language. Okay, so let's go a little bit deeper into sort of the functions of this computer. So the whole thing is run by a clock. So it just ticks on and off. So when the clock ticks off, we load a new instruction. So normally that just means incrementing the previous instruction by 1, but if we had a jump on the previous step, then it'll take what's ever inputted here and set that as our new address. So I'm not going to go into what every line of Redstone does, but this line here, if it's on, we jump. If it's off, we don't. We just increment. These lines give us what we want to jump to, but we don't use them if we're just going to increment. This whole thing sort of acts like a register. It's a little bit more complicated. If you were to build a computer in real life, you would have a register as part of this logic, but the way it works out to combine it with this sort of resettable set to that functionality with an increment, it's just not, it doesn't look like the registers over there. But either way, this value, this is what's known as a program counter. So it stores what value, which instruction we're at in the memory, and goes to the next one or jumps. So that's what happens on the falling edge of the clock signal. So we load a new instruction. The address goes out there. We read it back. Then it goes to this, which is the instruction decoder. So this just sort of implements the logic we were talking about earlier with, if figure out the first bit if it's data or computation, and then send out whatever signals we need. So up top here is what we read if it's a data instruction. It sends it out into this bus that holds data. On the bottom here is all the logic for if it's a computation instruction. You can see it's a computation instruction since all these values are going through. And these are just a bunch of wires for destination and the source memory bit and all that good stuff. And it also holds the opcodes for our computation. So this half of the clock tick is sort of full of a lot of stuff. We increment or jump, we get the new instruction, decode it in the instruction decoder, then the ALU gets that opcode, does the computation, goes through the ALU, then the value gets outputted, and it makes its way to the output of, say we're storing an A register, makes its way to the output over here. But then we wait for the rising tick of the clock pulse when it turns on, and then we're going to set that value into wherever the destination is going to be. So the way that works is we have an AND gate here. So one half of the AND gate is this destination signal. So if the destination flag for the A register is on, this turns on, and then this is connected to the clock signal, and this is just it gives a pulse. So when that line turns on, a pulse goes through, and then we set the A register to whatever value the output was. So in this way we can sort of the clock pulse is a way to synchronize the operations of the computer, because it takes an amount of time for computation to go through the ALU. Even with all these repeaters, it takes an amount of time for computation to travel from one end of the computer to the other. So in normal computers, they have a clock pulse as well, but it's clocked at megahertz or gigahertz, so millions or billions of times a second. My clock pulse goes once every 30 seconds, so it is much slower than any normal computer. But that's just because all of these components are so slow, relatively speaking, to a real-life computer. I don't think in this explanation I'm going to go into sort of a block by block, how each component works at a very base level. I might do that later if there's interest, but hopefully I've been concise enough and not rambled about how all of this works. I've done my best, and hopefully it suffices to give you a little bit of an overview on how computers work.